All right, here's your test number 3 review for Calc for Business. First thing we're going to do is differentiate a couple functions. So in this case, we're going to differentiate a function that has an exponential in it. Being that it has an exponential in it, you have to remember your derivatives of exponential functions. But that's not the only thing going on here. This is also a product. So what we're going to be using is the product rule. So when I take the derivative, I have two parts here. I have the x and I have the e to the negative x cubed. So you should remember your product rule. I'll take the derivative of the x, which is 1, times the e to the negative x cubed, plus I'm going to take the derivative of the e to the negative x cubed times the x. Well, e to the negative x cubed, you rewrite the exponential, then you multiply by the derivative of the exponent. So that would be a negative 3x squared. So this is multiplied by this e. So other than that, there's not a whole lot we can do here. A couple of ways we could write the answer. I could write this as e to the negative x cubed minus 3x cubed e to the negative x cubed. That's this times this. That's where I get the negative 3x cubed. I could write it like that. I could see that they both have an e to the negative x cubed in them. I could factor that out. 1 minus 3x cubed. If you want, this has a negative exponent. If you want to write it so it doesn't, we could also write it as 1 minus 3x cubed over e to the positive x cubed. Any one of these would be acceptable answers on the test. I really don't care which one you would give me, but this is not the final answer. So 1, 2, or 3, either one of those would be fine. Here's another one, in which case you want to find the derivative of y with respect to x, t, or theta. Well, in this case, since we have x's, we're going to take the derivative with respect to x. And so the idea, though, is this is a logarithm. So in order to take the derivative of the logarithm, we use our u prime over u rule. But I don't want to take the derivative of this whole thing. It'd be kind of messy. So what I'm going to do first is I'm going to use some of my log rules to rewrite the function. So y could equal log of 1 minus x minus 5 times the log of x plus 4. So that's taking the division and turning it into subtraction, and then this power coming out to the front of that term with a multiple. Now I'm going to take the derivative. So I have this log minus this log, so I can do each one separately. U prime over u. Here's my u, so the derivative of this, which would be negative 1 over that. Minus 5 times, same deal again, derivative of this divided by this. So that'd be 1 over x plus 4. So I could write my answer as negative 1 over 1 minus x minus 5 over x plus 4. For a test, that would be fine. There's not really much else we can do there. To simplify it, although lots of times you'll see it written as a single fraction, which would be 1 minus x times x plus 4, being the common denominator. So this will be negative 1 times x plus 4 minus 5 times 1 minus x, ultimately giving me what this will be positive 5x, this will be a minus 1x, so that'll give me a 4x. This will be a negative 4, and this will be a negative 5, so it'll give me a negative 9 over 1 minus x times x plus 4. So oftentimes you'll see that given as the final answer, but for the test, I think that would be just fine. All right, so we have some integration now. In this case, we're just doing indefinite integrals or antiderivatives. So polynomial, this should be one of the easier ones you do. In which case, if we're doing the integral of this polynomial, since they're added together, you could do each one separately. The constant multiple 7 and the 8, they can come out. So in which case, I'm going to get 7x to the 4th over 4 plus 8x squared over 2 plus 7x plus c. And if you're not sure that that's the correct answer, take the derivative of this and you should get back to here. Here's another example, a little bit more difficult. What I'm going to do is rewrite this one first before I do an antiderivative. As is, it's going to be very difficult. So what I'm going to write first is everything in exponent form. So this will be x times x to the 1/2 plus x to the 1/2 over x squared dx. Then these two come together to give me x to the 3/2 plus x to the 1/2 over x squared dx. Then what I'm going to do is split this apart into two separate fractions. Okay, I'm going to write this as x to the 3/2 over x squared. plus x to the 1/2 over x squared, all dx. Then I'm going to simplify each one of these fractions. So I'm going to subtract the exponents, in which case I'm going to have an x to the minus 1/2, and this one's going to be x to the minus 3/2 dx. Now that I have it in this form, this is the easiest form of this function to integrate. Now I just integrate each one separately using power rule. So sometimes you have to manipulate your function before you integrate it. So what I end up with is going to be x to the 1/2 divided by 1/2 would be multiplied by 2, plus x to the minus 1/2 divided by minus 1/2 would be multiplied by a minus 2, plus c. So I'll clean this up a little bit. 2x to the 1/2 minus 2 over x to the 1/2 plus c. And that's going to be your answer. You can change these x to the 1/2 as into roots, so I could say square root instead of the 1/2 power, but I really don't care which way you write it, root or exponent. All right, here's one we're going to have to do more by substitution than anything. We can't really rewrite the function in any other way that's going to be helpful for us, but we can do some substitution, in which case I'm going to say that u equals 7x squared plus 3. The derivative of that would be 14x dx. Now notice, if this comes out to be u, that'll be u to the 5th. What's left over is this x dx, but I don't have this to be x dx. I have 14x dx. So I can easily move this 14 over to the other side by dividing, in which case this integral will become the integral of u to the 5th over, under du over 14. Now I could put the over 14 here, but I'm going to put it out because over 14 is a constant multiple. So now if I go to integrate this, I have 1 over 14 integral. I'm going to write this as u to the negative 5 du, so now I can use the power rule. And now it's really easy to do. So in which case I get 1 over 14 times u to the negative 4 divided by negative 4 plus c. Well, 14 times negative 4 equals... we got 1 over negative 56 times u, which was 7x squared plus 3 to the negative 4 plus c. If you want to go one step further, I can write this as 1 over negative 56 times 7x squared plus 3 to the 4th, all in the denominator, plus c. Being that this is a negative exponent, I really should bring it all to the denominator, and there's your answer. Here's one where we can do another substitution. Usually when you see logs inside your integral, it automatically tells you want u to be the logarithm. So this is log of x to the 6th. I want that to be my u. Because differentiating a log is something we really haven't done. Integrating a logarithm is something that we haven't done. We've differentiated logarithms. So we're going to take the derivative of the logarithm, in which case what I'm going to do here is I'm going to bring this power out to the front first. So it's going to be 6 log x. And so my derivative is going to be 6 times 1 over x dx. Now if you look, if this comes out as my u, what's left? I have a dx over x. Well, 1 over x dx is dx over x. So I have everything here except for this 6. Similar to the last problem, I'll divide by the 6. So what do I end up with here? Dx over x is du over 6. So the over 6 I'll put out here. And then this was u, and so that's sitting in the denominator as my u. And so now what I have is the integral of du over u. Well, if you remember, that is the derivative of a logarithm, right? We took the derivative of the logarithm, we did 1 over u, dx over x, du over u. It's all the same stuff. So this will be log of u plus c. So then I get 1/6 log of log x to the 6th plus c. Here's a similar one, same idea. I want u to be my logarithm. I could write that as 4 log x, so that when I go to take the derivative, I have 4 times 1 over x dx. Again, 1 over x dx is dx over x. I have a dx over x. That's the u I just used. So this one turns into u du over 4, because this 4 is going to divide. And so I'm going to get 1/4 u squared over 2 plus c. Well, the 1/4 and the 1/2 is going to give me 1/8. U was log of x to the 4th squared plus c. Okay, let's look at this one. Another substitution. You got to recognize these as substitution because you see a function and that function's derivative inside the integral. So if I let u equal 2 plus 3x cubed, the derivative is going to be 9x squared. Now I got a 10x squared instead of a 9x squared, but we can make that work. So this 10 is a constant multiple that I can pull out, and this 9 is a constant multiple that I can divide. So if you look at this, if I pull the 10 out, I have x squared times the 4th root of 2 plus 3x squared dx. So if this is my u, x squared dx is going to be my du over 9, and this 10 is just sitting there, so I get 10 over 9, 4th root of u du. Now 4th root is 1/4 power, so I'll write that as u to the 1/4 power du. And then I can just use power rule, so I get 10 over 9, u to the 5/4 divided by 5/4. Well, divided by a fraction, we've done this a bunch of times, you're going to flip and multiply, plus c. So I'm going to have 4/5 times 10/9 times u, which was 2 plus 3x cubed to the 5/4 plus c. Now what I can do here is I can cancel this 5 and this 10. I'm left with a 2. So ultimately I end up with 8 over 9, 2 plus 3x cubed to the 5/4 plus c. All right, so this one, now we're getting into the definite integrals. So this one says find the total area of the region between the curve and the x-axis for y equals x squared plus 1, where x is between 0 and 1. So if you were to sketch this out real quick, you could get a really easy graph done here. X squared plus 1 is a parabola up 1 unit. Everyone should be able to handle that pretty well. Here's x of 0, here's x of 1, so it's bounded by the x-axis. Up here, up here. So this is the area we're trying to find. So we talked about these are the rectangles here. But rather than adding up those areas of rectangles, we talked about how this area can be found by doing the integral from 0 to 1 of x squared plus 1 dx. By taking this function, which is this y equals x squared plus 1, bounded by the x-axis between this interval and this interval, that area can be computed using this definite integral. Now, as far as the definite integral goes, the idea is first we need to find the antiderivative of this. That's pretty easy. It's going to be x cubed over 3 plus x. Remember, no plus c needed here. Then we're going to evaluate it between 0 and 1. So I plug 1 in, which will give me 1/3 plus 1, minus I'm going to plug in 0, which will give me 0 over 3 plus 0, so that's just 0. So 1/3 plus 1 is 4/3, so that area right there is 4/3. Okay, in this question, they weren't asking you to find the area. They're just asking you to do the definite integral, in which case we're going to use some substitution to get this done. I could multiply this out and do it as a polynomial, but it's actually easier if I say u equals x plus 2. Du is the derivative, which is just 1 dx. And so I can turn this into the integral of u cubed du. Now the trick with substitution is that this is 0 to 3. So the idea here is these are x values. We just switched over to u's, so we got to be careful there. So what I'm going to do is I'm going to find the antiderivative, which will be u to the 4th over 4. We're still between 0 and 3. Remember, no plus c is necessary. I'm going to resubstitute in my x plus 2. Now that I'm back to x, and remember, these were x values from the start, now I can plug them in. So I'm going to say 3 plus 2 to the 4th over 4 minus 0 plus 2 to the 4th over 4. And so what I end up with is, what's this, 5 to the 4th, which would be 625 over 4 minus 2 to the 4th, which would be 16 over 4. So I get, what's that going to be? It's going to be 609 over 4. Okay, here's another definite integral. Again, we're going to have to get this one done by some manipulation. In this case, not substitution though. I'm going to treat this one similar to the one we had earlier with the x to the 1/2, where we split it up. So I have 1 over 4. I'm going to write this as t squared over square root of t, which already is t to the 1/2, plus 1 over square root of t, t to the 1/2, dt. The idea is I split this over this and this over this. Okay. Now, the reason I did that is because now I can simplify this fraction. If I simplify that fraction, that'll give me t to the 3/2. And if I bring this up, it'll give me t to the minus 1/2 dt. So now I'm going to integrate, in which case I'm going to get t to the 5/2. Divided by 5/2 means multiplied by 2/5. Then I'm going to have t to the 1/2 divided by that would be times 2 between 1 and 4. Now we never did substitution here, so from the start these two were t values and we're still having t values, so now I could just plug it right in. So I'm going to get 2/5 times 4 to the 5/2 plus 2 times 4 to the 1/2 minus 2/5 times 1 to the 5/2 plus 2 times 1 to the 1/2. Now 1 to any power is 1, so that's easy. Now this one should be pretty easy too. 5/2 is 5th power second root. Well, second root of 4, if I do the second root of 4, I'm going to get 2. Then 2 to the 5th is going to give me 32. So I have 2/5 times 32, plus I'm going to do that again here, but this is just the square root of 4, which is 2 times 2, so that's going to be 4. This will be minus 2/5 plus 2. Right? Actually, sorry, that's wrong. This whole thing is being subtracted. So that negative has to distribute in there and there, so this actually is a minus 2. So what I end up with here is this will be 64/5 minus 2/5 will give me 62/5. 4 minus 2 will give me 2. So that's going to be 62/5 plus what, 10/5. So that gives me 72/5. All right, so here, this one's probably the easiest one of the bunch, in which case we got to do this definite integral, but it's just a polynomial. So this should be really easy to find the antiderivative. If we look at this thing, we could just go right at it. We can say 8t plus t squared plus t cubed between 5 and 7. Plug in 7. I'm going to have 8 times 7 plus 7 squared plus 7 cubed minus plug in 5. 8 times 5 minus 5 squared minus 5 cubed. Now the hardest part of this whole thing is probably just doing the arithmetic part. So the 8 times 7 will give you the 56, plus 7 squared is 49, plus 7 cubed is 343, minus 8 times 5 is 40, minus 5 squared is 25, minus 5 cubed is 125. So if we do that computation there, what do we end up with? So it's 56 plus 49 is 105 plus another 343 gives me 448 minus 40 minus 25 minus 125 ultimately gives me what's that? I'm getting 258 out of that. So I mean, again, that's probably the hardest part of this whole thing. The integration should have been real easy.